Hello, my name is Beth Dixon, and this is a video series based on Vicki Borlaug's PowerPoint presentation on the complement rule and the phrase "at least one." I wish to thank Mrs. Borlaug for allowing me to use her PowerPoint to make this set of videos on the complement rule and the "at least one" phrase. I anticipate that this series will be 2 to 3 parts. We'll have to see as it goes, and I'll probably add a little call out to let you know. But this is part 2 of the series. And our next topic is the phrase "at least one." And we're ready for example 3. A couple is planning to have children. They have the probability of a child with blue eyes is 0.25. If the couple has 3 children, find the probability that they have at least one child with blue eyes. You may assume that there are no identical twins or identical triplets. A couple is planning, whoops, I'm reading the problem again. Sorry about that. Let's talk about our notation just quickly so that you'll not get confused a little bit later. And like I always say, mathematicians love their notation. We have B for blue eyes. N is not blue eyes. So what is the probability of blue eyes? Well, looking at our problem, the probability that this couple has a child with blue eyes is 0.25. What is the probability of not having blue eyes? Well, that would be the complement, and that would be 1 minus 0.25 or 0.75. And in problems of this nature, you may use both numbers, you may not, but it is always a good policy to go on and find both probabilities as you start the problem. Now, the next thing is to consider our sample space. We will do this in this first example, but no, you will not do this for every problem that you do. But this is to help illustrate what to do when you see that phrase, "at least one." So we have the sample space. One possibility would be that all 3 children have blue eyes. Next would be that 2 of the children have blue eyes and one of the children do not. And that child without blue eyes could be the first child, the middle child, or the last child. Then you could have only one with blue eyes and the other 2 children not have blue eyes, and the one with blue eyes could be the first child, the middle child, or the last child. And lastly, you could have no children with blue eyes. And this consists of all the possible ways to have 3 children, either with blue eyes or without. Which of these families has at least one blue-eyed child? And let's circle those that have at least one. Well, 3 is at least one. Anything more than one or more, anything more than one or more. 3 is more than one. 2 is more than one, but even 1 is at least one, so everything that we've circled here is at least one blue-eyed child. Well, what is the probability for each of these families? And we can calculate that. What's the probability that you get 3 blue-eyed children? Well, that would be 0.25. 0.25 times 0.25, because the probability of being blue-eyed is 0.25. Well, if we have a not blue-eyed child, that's a tongue twister, and a blue-eyed child and a blue-eyed child, The not blue-eyed child is 0.75. Whoops, I forgot to tell you that that gives us a decimal of 0.015625 when we multiply. But next, moving on, not blue-eyed is 0.75. Then times a blue-eyed child, which would be probability of 0.25, times the probability of being a blue-eyed child, 0.25, and if I multiply those three decimals out, I get 0.046875. Moving to the third family with a blue-eyed, not blue-eyed, blue-eyed, that would just be 0.25 times 0.75 times 0.25. And it's just a rearrangement of the previous one, so we get the same decimal. The third family, blue-eyed, blue-eyed not, is still just a rearrangement, so we'll get that same decimal again. Moving to the next family, we get a different set because we have a blue-eyed followed by two non-blue-eyed, so that would be 0.25 times 0.75 times 0.75, and that would give us the decimal 0.140625 for one blue-eyed and two not. Then the next two are just rearrangements of those, the not blue-eyed, blue-eyed, not blue-eyed, the not blue-eyed, not blue-eyed, and blue-eyed. And that is such a tongue twister. I hope that you're seeing that despite my tongue twisting words. So, what are these probabilities? These are all the ways to do it. Well, what would we do with these? Well, we would need to add up all of these probabilities because all of those would be at least one child has blue eyes. So to find the probability of having at least one blue-eyed child, we must add up these probabilities. At least one blue-eyed child, and we would add up those decimals. And that would give us 0.578125. And that would be our answer. You can see that even this, as small as it is a cumbersome way to do it. But there is a much easier way to get this answer, and aren't we glad? We can use the complement of at least one. Notice that as we look back at our sample space, we circled all but one of the families. We did not circle the last family, which was the family that consisted of no blue-eyed children or three not blue-eyed children. This is the complement of at least one blue-eyed child. We can easily figure this one probability. The probability of not being a blue-eyed child is simply 0.75 times 0.75 times 0.75, which is 0.421875. And since those two have to be related, how? Well, since they're complements, they have to sum to 1. And if we knew just the 0.421875, we could subtract from 1 and find the answer. So we will redo this example using the complements, and this is what you should do to do the problem. The probability of at least one blue-eyed child. Look at what your at least one blue-eyed child would be, and not at least one blue-eyed child. Another way to say this is all or not blue-eyed child. So 1 minus the probability of not being at least one blue-eyed child, And what is not being at least one blue-eyed child? That they all are not blue-eyed, and since we're doing 3 of those, that'll be the probability that the first is not blue-eyed, the second is not blue-eyed, and the third is not blue-eyed. So that would be 1 minus 0.75 times 0.75 times 0.75, and that gives us the same answer that we got before. Why would the solution that was presented be wrong if in fact we had identical twins or triplets? Well, Ms. Borlaug put this here, and I think what she was after is that identical twins and triplets would actually have identical genes and therefore not actually be considered separate children. I'll have to ask her about that. Think about that question. This is a very good stopping place, although we've probably not done enough examples on this to actually grasp the whole part. So you will definitely need to watch part 3 of this to get a better grasp on the at least one concept, which is one of the harder concepts that we cover. But thank you for watching this part 2 of this video series on the complement and the phrase at least one. If you need additional help and are a Walter State student, please come by and see me in the math lab in MBSS 222.